All right, now I'm ready to interact with you all. Sorry. There's this. Okay, so at this point you should understand at some level that the goal is to try to relate spaces. All the spaces that we will talk about are filled with whatever we call a vector. And vectors at least have to have two operations going on. So we think of V, the vector spaces. They must have an addition, and then they must have a scalar multiplication. Now the scalars can often be derived completely from the addition, which makes it simpler to find it in real life models. You can just simply say, iterate the addition, do the addition several times, call that scalar multiplication, and the consequences follow. Now that may not be how you think of it, and let me also go ahead and say a couple words about some other language. There are other things out there called modules, which is another more expansive term than vector spaces. And this is for people who really want to be delicate about what properties they want to assume when they describe the addition and the multiplication. For example, do they want to allow that there are always fractions of your numbers? In vector spaces, there will always be fractions. And that's really the only difference between calling something a module or not. I don't think you gain much by thinking of these as separate. Almost every mathematician I know, upon saying modules, proceeds to talk about given V in the space. So it's one of these things where we made a big fuss about making a difference and then we forgot about the fuss. Okay, so long term, I think that fast forward 20 years, vector space will be used interchangeably with module. It is in transition, so I want to recognize that you will still find books that make a big fuss about these two separate words. Okay. Our process is to understand linear algebra. Algebra has to do with operations. The linear part has to do with having those two operations only. Okay? So that's where we are. Now, it's not fun to look at just one vector space. When we do that, we have words like affine and projective, and we can model a lot of things in that. But the real fun happens when you compare two different vector spaces. That's when you have interactions. Or maybe 3, or 4, or 10, or 1,000,000, or an infinite number. When you start asking for interactions of linear algebras, different vector spaces, you need them to at least talk to each other amongst their operations, their pluses and their scalars. And so what we can think about as a general idea is that I could have one vector space that I call V and another one that I call U, and I have a translation from one to another. Maybe it goes in a direction, we'll call that a function. There are plenty of situations where you want to do more than just relate them by a function, but today we're going to focus on this and its friends. Now that would be fine, but this wouldn't necessarily have to carry any of the information of the algebra of V to the algebra of U. So what we start to do is we say, well, whatever the algebra is doing, when I add a pair of vectors, and this notation says simply to think of the things as pairs. So this could be a V1 and a V2, bless you. Right? I take two vectors, I pair them together, and I create a new vector called V1 plus V2. Okay? That's all that this is trying to say, and it's trying to give it to you in a language that you can try to compare things. It's a good flowchart type language. U is supposed to have its own addition, right? These don't have to be the same. This one I'll put a V on, that one I'll put a U on, just to remind myself that maybe these are, over here, supplies, and over here are client orders. Those don't even have to have the same shape. Those can be completely different looking vectors, and we're looking for a comparison between the two. Now, I gave at the beginning some translation of, say, supplies converted to making something, client orders, but that doesn't carry the algebra unless I can actually continue this pattern along. I can move that same function f here and the same function f here in my flowchart. Now let's try to digest what this actually means. I'll draw this in color so you think of this in motion. V1 goes through this translation, this operation that changes the numbers around somehow. And I don't know how, so I'll just call it for now f of V1, just like I would talk about square root of 2 or something like that. It's applying some transformations to some numbers to produce new numbers. But it's not just one input that I have to addition, is it? I have a left and a right-hand side. So I want to apply the second f to produce a second number. Okay? So over here what we did is we added these two up and got that answer. And now we could come over here and compare that addition. We could compare the addition of adding the f's together, and we know what this answer has to look like. This is f of v1 plus f of v2. So far, nothing has happened that we need to worry about. But what could we now ask that would bring together a constraint and not let us just do whatever we want to these spaces? If you look at this, there are several paths to the same place. Right? I can go across here and come down, or I could first come down and then go across. The results won't be syntactically the same, meaning I'll write different amount of chalk. Syntax just means what does it look like. It doesn't mean you understand what it means, okay? And we'll add meaning to it, but we're just simply saying, do these look the same to us? And the answer is no, they do not look the same, right? I did different squiggle marks, right? If nothing else, they're not the same symbols. But now we ask ourselves, well, whatever they mean, at the end of the day, this means some vector in U, right? This is the U addition. And what does this one mean? That means some vector in V. These are two separate additions, but by applying the function f in judicious ways, applying it to the u parts or the v parts, applying it always to v parts, but applying it to the individuals versus their sum, allows me to make a question out of this. Are these the same? Did they come out the same? If this happens, then I would say in some way that the algebra of addition on v is compatible with the addition on u. I mean, it's just a definition. It's just my sense that they're not so crazy that I can't put an equal sign between them. Okay? And when I get to put an equal sign in there, that's going to tell me that this translation between my data is somehow fruitful. It's helping me understand one algebra in terms of another. And that we call linear. Well, maybe we want to sneak up on it because we do have this extra scalar. So maybe before I call it linear, I should just call it additive. That would be a better name anyway. You can see it behaves well with addition. Another term that you might use is you might just call it distributive. Okay. Once we have that, we can pose the same question for the other operation. You can do this. You can do it. Let's do this. For those of you who are joining us on Makeshift Online, so the university has $1 billion endowment, and this is what they give me. Let's take the scalars and put them into the storyline. So help me out now, because the whole goal here is not for me to just tell you what you need to know, but to tell you how to go find what you need. I just decided that I wanted to relate V and F, two vector spaces. And at the moment, they were just two collections of data. So I made some translation, a function from one to the other. That was the collection of data that I wanted to compare. But then I worked harder to stipulate what I meant by it interacts with the addition well, that the addition in U and the addition in V are compatible. But there's other operations going on here, the scalars, right? What would I need to draw to give a similar storyline to scalars being compatible? Yes, Anton.
Could you make it so instead of V1 and V2, it's V1 and V1? So then you have...
Are you talking about the little elements here?
Yeah.
Could we start with the big elements and then I'll come back to the little elements? I'm going to suggest that we want to talk about F being somehow, the way we translated, that F is compatible with. So I want to use F still. I still have V to U with the same transformation. But I now want to talk about how scalars interact with this function. How do I scale a vector? I put a symbol in front of the vector, and then it returns a what? A scalar, a vector, an elephant? Another vector, right? In what place? In what space? Same space. So up here are my decimal numbers, or if you like, replace that with your thing k. Whatever coordinates you want to use for your number system, k is fine. But if you don't know any other number system than the real numbers, the decimals, just use that. No harm. When I multiply a vector by a scalar, it becomes just another vector. It's a different vector, most likely, but it's just another vector. Okay? I'll put a little dot on the name of that function. All right? The arrows are here to try to track how we're moving data around. It's a flowchart. It's nothing deeper than that, but it's a mathematically driven flowchart. Okay? U also has scalars. Now, in the pattern we had over here, you could see that I just copied f everywhere that I could. Now over here, what can I do? Can I put f anywhere else?
Sure.
Sure, where? The bottom row. That's a place where there's another v and u, and you could say, maybe I want to translate the data there. Could I put f up here?
No.
No, it's not the same kind of data. So this is what we call heterogeneous data. Heterogeneous operations. And over here, this would then retroactively be known as homogeneous operations. Because on the addition, everybody came from the same place and ended in the same place. In scalars, they came from a mix of places and ended in a mix of places, okay? You might even fine-tune that to have degrees of how heterogeneous and homogeneous it is. I leave that to you to explore. Just splitting it up as two families is an important step, okay? Now, what this means is that if I try the same game that we already had, we try the game out, what we did before is we took all the possible inputs here, shoved them in two different ways. So over here, I'd have a scalar lambda and a vector, right? That's the data I would have. And I would scalar multiply them to get lambda dot v. That's what this thing does. And I hope you're seeing me use a slight change in notation, very, very subtle. And I want to emphasize it. You see this difference here? The little flat line versus the straight line? This is not all that important except as a way to check that you're doing something right. It's just an extra little like error correcting code for yourself. Notice that when we do algebra, we have little letter algebra, and then we have big letter algebra. Big letter algebra are the spaces. Little letter algebra are the things inside the spaces. Okay? And what you have to sometimes do is clue yourself into what are you trying to describe to each other. And it can get really confusing whether you mean big letter or little letter reasoning, right? So for example, I could talk about adding two spaces. Add two lines. Two lines determine a plane. Do I really mean adding two lines? Or do I mean something like, well, these are big lines and then there's a thing that is their whole span? Right? That's a different addition than taking two vectors and adding them. So because we often want to recycle our language and reasoning from the little letter and big letter, we draw a distinction between the two. And so for that reason, as an added aid to make sure I don't confuse myself and those around me, when I'm moving the big letters around, I just use an arrow. And when I'm moving the little letters around, I put a little tail on the arrow. That's just a convention that mathematicians agreed to in their flowchart language. Okay? There might be deeper things. You can go to another class and find out. But that's for this class, that's plenty. Okay, I could do that. I can move some of these data around. So for example, I can take lambda v and apply f to it, and I get this. I can move v over to here and call it f of v, but I'm missing something. I can't play the game we had because how do I move the lambda over? So what do we do to fix that?
So you apply lambda to f of v.
If I do that, what am I doing? I'm moving the lambda over to here. So you want me to just keep the same lambda, right? And if I keep the same lambda, that's the same as using the identity function.
F of lambda? You want F of lambda?
There is no f of lambda. F only applies to vectors. Lambda's not a vector. Lambda's a scalar, right? So Shu's idea, let's try it out, is to just say, well, just reuse lambda. Don't change the top line. You didn't tell me any way to change it, and they're the same number system. They're both decimals. Maybe just don't change it at all. If you're not given any way to change it, then don't change it, right? If you're not messing with it, don't mess with it, right? So lambda becomes lambda. But we did actually fill in the top arrow with something. It was missing. We took a hunch. Maybe don't mess with it. Now we could actually compare the two. Take lambda times this, and we would get, as a result, lambda v, okay? The subtle difference is, this lambda lives in what vector space? This scalar multiplication, that's the v1, and this scalar multiplication is the u1. So once more, if we arrive at two different places, they don't have to be equal, but if we're looking for functions that play nicely with the algebra, then we'll say the ones that play nicely should be equal. And this is a way of saying that they must relate one scalar to another. And when we add this in, we say f is a scalar invariant function. Okay? And so the combination now will be the more powerful mixture, but you can see that there's now two separate algebras, and we've come up with two separate tests. Right? One was homogeneous, so we applied f everywhere, and we saw that they played along well. That was the additive. One was heterogeneous. We had to come up with an extra function that was different than the other ones, and then it played well with respect to those functions, and we got that it was scalar invariant, just as a lingo jargon for this. F is called linear if it is both additive and scalar invariant. Okay. Retroactively, for those of you who do other types of mathematics and you deal with algebras of some kind, when you have something that respects homogeneous operations, these are often called homomorphisms. If they also respect heterogeneous operations, they're called heteromorphisms. I won't use that language in this class. Maybe in passing I might accidentally say it, but this is mostly to ground it in concepts you might be seeing in other classes or you saw before. Okay? Any questions before I move on? So linear is a way to relate two vector spaces. It has to take into account all the operations, and that's what it's done. Now, what if you don't think we're done? What if you say, no, Professor Wilson, there's other things I do with my vectors. I sometimes negate them. Maybe some of you do. How would you add that to the story? I'll give you a head start. Try to write down what you think the flow chart would be for taking a vector and negating it, and then compare that to a translation from one vector space to another with an F. What would you write down? That's the object of study, is my function that's translating one vector space to another. I've just invited to a party a new operation negating things. How many inputs does a negative need? You need 2 things to negate something? How do you take the negative of 7? Well, you could think of it as multiplying. So there are relationships. We'll come up with the relationships in a second. But just if I just want to talk about negative 7, I just need the 7, right? I just need one input, and then I put a minus sign in front of it, right? So when I have a vector and I want to think of its negative, like it's pointing here and I point it down, I just need how many vectors as input? 1. So these are the inputs to my data set, right? So if we're doing the cartoon, that's the data set. Next frame in our cartoon, we're going to add on to things. For those of you who don't remember or maybe I don't know what I say in every class that I teach. So let me just make sure that this is clear. When drawing diagrams, they often evolve over time. And that means that you need to somehow make freeze frames of what's happening. Otherwise, you just see this completed picture and you don't really know what the story was that goes with it. Fortunately, comic book writers solved this problem. They just have frame 1, frame 2, frame 3, and you just kind of draw and update your picture. It takes a little bit more time to draw it, but then when you look back at your notes, you know what's being said. So that's what I'm drawing. It's the same picture, and then I'm going to add to it in each frame. Okay? And you might put captions or something, right? I would love to see linear algebra as a comic book, just drawn wonderfully. I can put F down here, and I could ask for the negation in U, right? That's something I could now write, because I know that my vectors are going to have negatives. So I might as well compare. Are the negatives for the vector spaces compatible? That's our general jargony thing. Now, we don't use the word compatible anymore. We use words like, is it a heteromorphism? Is it a homomorphism? Things like that. We're trying to say, like, in what sophisticated sense are they compatible? But compatible is the big idea. Do they go to the same place if you apply them in different orders? And so we can just follow our nose. Right? I say, well, I take a little vector here, and the first thing I do is I negate it. And then I apply F. But maybe I first applied F. So now it's a U thing. And then I negate that. And you'll see that you get that's a V. You get 2 different sets of symbols, right? They're not the same symbols. So therefore, there's a chance that they could be different. And there are examples where they are not the same. So when you want something to be compatible, what would you want as a conclusion here is you'd want to limit yourself to the functions where they are equal. Okay. So when you see an equation involving functions, what you're really doing is you've got a little flow chart where things go in the information in one way and another way, and they end up at the same place. So the equation is that 2 paths lead to the same place, and they're considered equal. Okay? Now you know that in real life that's not actually true, right? You can walk directly here, or you can beat Professor Wilson by I don't know how. Running, going through tunnels. How did you get here? It was something magical that happened there. So thank you for collaborating in the lecture, though, by giving me 2 paths to the same place. So. Trent and Matt got here before me, but left at the same time. So. Okay, so do you see how to build these general patterns? You build them all throughout your life. There are lots of things you have to add to your algebra just because it's appropriate for your situation. And when you make a modification, at first it can feel like, I have to go learn a whole new thing. Yes, you could go learn a whole new thing. Or you can maybe bottle up what's going on here, which is you just have a flow chart, 2 paths to the same place. You write down the appropriate qualities for your problem, then you add that to your story, update that to your story. Let me show you one version of that adaptation so that you get a little bit familiar with it. Let's go back to this one over here. And let's say that maybe we refuse to use the identity on the real numbers. In fact, I'll give you an example that happens in real life. All of this is pseudo-real life. I know real numbers aren't real. It's like every number you ever write down stops somewhere. So, complex numbers, they take decimal numbers and they add to it in another direction the square root of minus 1. And as I've hinted throughout the course, we don't know which square root of minus 1 we use, right? We just pick one. We just sort of decide. The one that's pointing up we call the positive square root. The one that's pointing down we call the negative square root of minus 1. There's really no way of knowing. They're totally arbitrary symbols. And because of that arbitrariness, in some situations, it doesn't matter what you pick and everything just comes out the right way. In other situations, you end up with this trouble of needing to swap between the two of them, which you do with that bar. We call it complex conjugation, and the idea is that you flip the minus sign on the square root of minus 1. And it's used throughout all kinds of sciences to fix little problems where you made a choice that you don't actually have the right to make, but you need to write something down. So then you give yourself the option to flip it when it's the wrong one. Now that would not be the same as leaving the scalar lambda as lambda, would it? Swapping would put lambda bar here. And it would no longer be the identity, the equal sign between the scalars, but it would be complex conjugation, which doesn't have a convenient function name. I'll just call it sigma, just to have a name to put on that arrow. Change, update everything to match this information. Well, nothing down here changed, but things up here did. In particular, we now have a bar on the lambda. We've swapped the directionality of the square root of minus 1. So now when we multiply them out, if we want them to come out as equal, compatible algebras, we don't mean for lambda to come out unscathed. What do we mean for it to do? We put a lambda with a bar in front. This will happen throughout mathematics and models of mathematics. You'll find examples where you need to do a small modification. Don't panic. Draw your pictures. Write down what you need to have happen, and you'll get the equalities you need. They will keep changing. Just update everything. This particular one is pretty common. It has its own little name. Whenever you have to change the scalars by applying something like a complex conjugation, instead of calling it linear, the community agreed to call it semi-linear. Yeah, we could have called it quasi or pseudo or any number of things, but they say semi-linear, and that's the word. Okay? So you'll have plenty of applications where you'll see semi-linear transformations instead of linear ones. They're just about linear. They behave just about the same. They're doing just about the same things. And you can see the small modification was no longer the identity at the top, a more interesting function. We're good with that? Okay, now that we have that, let's go back to our tensors and our fundamental spaces. Try to make sure I'm on the board that's being visible to the camera. Now where we left off was we had this, what if you want to pair more than two spaces, right? We didn't want just one vector space. You wanted 2, 3, 10, however many vector spaces. But this isn't bad in terms of compatibility. This is a pretty good storyline because you can see how to match up the pieces of one vector space with one other vector space. So that's going to be a good translation to have, but now we're going to have it between many vector spaces. Okay? So now let me recall the notation for us. We have V1 through VL, some number of vector spaces that we're comparing. In the storyline that we've been following with the Nabisco tensor, we only had 3 spaces. The plants, the foods you could make, and the clients that would order it. You could add nuance to that and break those up. That's your call. But there's several spaces. And then the output, I worry this whole chalkboard will fall apart on me. So the output in that situation was just some scalar number. We were just trying to say how much of Oreos are being made in the Chicago plant for Kroger. And that should just be some number. Okay, so it just ended in some number for that particular storyline. It could end in something else, but that's the storyline we have. And that tensor I was mentioning, you tend to use the gamma symbol for because it's got a little place to park the bicycle, right? Put all the little indices as subscripts underneath the roof, they don't get wet. It's an important problem, spraying water on top of your formulas. So, how would I now adapt what I've just done to compare this data, this tensor, to some other tensors? I saw this, and that's not bad, but that's exactly right. But let's put some things to that. Okay, you got to have some other vector spaces to compare to. Okay, some other tensor, also with different vector spaces, u1 through ul, also comes out with some decimal number. Okay. Now, you might ask, what storyline could this ever be about? I could give you lots of storylines, but let me just give you one, just as a prototype. Often what you want to do is compare the schedule you had last year to the schedule you had this year. Are you doing better, worse, whatever? So it's not even that this has to be a different vector than the one, or sorry, a different tensor than the one you already had. You're comparing it at different stages. And so you have actually different tensors because one was the Friday's schedule and the other one is Monday's schedule or something like that. So there's lots of reasons that you end up comparing tensors to other tensors, but that's just to give you one sort of foregoing example. Now, let's do this F game. I put an F here, right? Can I put the same F down here? Maybe. The problem is, if this is orders and this is plants, there's no reason for those to be the same vector space, right? They represent different data. So how could the same transformation be applied to them? It can't be. So what ends up happening is you end up with many functions between things. And likewise, we mentioned you could put a function down here that's interesting or boring. Typically with the real numbers, we tend to just keep them the same. But you could change that. You could rescale it. You could do something there. I'll just call that one F0 since I don't have a name. Okay, and then since this one's gamma and I want to compare things, I'll use upsilon for this one. Okay, you can park your bike on both sides. So you're learning how to build shelters while also doing mathematics. So. Okay? Now, what I want to try to do is exercise our notation and then talk about the fundamental spaces. That's what my goal is. So let's go back to the notation that we introduced on, would have been Monday, Wednesday, someday in the week. We used this notation. We snuck up on this. We just started getting to this. And we gave this notation where the way to evaluate gamma, you could think of it as iterating contractions one after the other, but it turns out it didn't matter which path you took, so we just put all the contractions in at once. So we sort of separate gamma from the things we're going to contract it with. V1 through VL. That was our notation for stuff in the vectors you want, come out with your answer, right? So now with that notation in mind, here's V1 is in V1, VL is in between there, and then any other spaces in between, you have a vector for each one of them. Are we good with that? I apply the tensor all the way down to get gamma of V1 through VL, which is a lot of little individual steps. There's a lot of little sums going on here, right? Each little one rescales all those slices and adds them up, making a smaller tensor. Then rescale those columns and add them up, making a smaller tensor. Rescale those rows, add them up. Finally, you get a number, right? There's a lot of math happening here. Guess what? Machines do it for us. We don't have to know. We just type in this, and it works, okay? Type in words like apply gamma to V1 through VL, and it works. And I don't know how it adds. It just does. GPUs and stuff like that. Just say words like GPU and your boss will be happy, right? So it does its thing. All right? That's on one side. I'm lying. I actually know exactly what it does. That's what my life is doing that stuff. But I don't want to talk about it is really the more accurate thing. But if you need to talk about it with somebody, if it would improve your life to talk about what's actually happening there, you can talk to me about it, just not in class. Okay. I want to move it over. Just take a guess. Now, some of you did not write last time I told you to take a guess. So now you're on my bad side. Right, Shu? You got to write stuff down. You got to write stuff down. You got to practice with your fingers. Otherwise, it doesn't become your knowledge. Right, Parker?
I don't know which one.
Everybody try to write out what you would do to finish this picture off. I want you I want you to learn, Matt. What do I want? I want learning. I just put my headphones on, just talk to myself at the board. Here we go, everybody. Da-da. Oh. Anybody missing a crescent moon earring? Any of our
that
online
on the
visitors
chalkboard?
missing that? It was in the tray. Probably belonged to some chalk. Yes, Anton?
How were you able to keep the same F when you were doing addition, but having to change up the Fs now?
Anybody have an answer? I don't know if I have the addition one preserved or not. I do not. Let me rewrite the addition one so that I can compare it. When I add vectors of the same families. For example, here's what I don't do. I don't add 1, 2 plus 3, 7, and 9. Because I don't know what you would want me to do with that. They're not lined up. Now, it's not that you couldn't go away, invent something. Like maybe you just stick a 0 underneath one of these or something. But that's a little bit unspoken knowledge. You'd have to explain how you want to add them. If I have the exact same families, then there's a kind of a more direct, obvious thing you might be meaning. Group like with like. Top row with top row, second row with second row, right? That's homogeneous. The data comes from the same family. They're both vectors of size 2. So that means that it's the same vector space here, and it also comes out the same. That's not true of everything, right? Scalars didn't look that way. Scalars took a scalar number times a vector. That's heterogeneous. That's multiple types of data combining to make some other type of data. There's going to be lots of things in your life that change shape, but addition tends to stay the same shape. It's usually a homogeneous operation, meaning that the type of data you feed in doesn't change on you. The inputs and the outputs are the same. Because they are the same, I have the ability to use the same function in every spot. Now, it doesn't mean you couldn't be creative and turn this into an F1, F2, F3, and some people do. But then that's changing the story around to a lot of more complicated things. Here, I just want to talk about one function comparing these two vector spaces. Okay? So since this is homogeneous data, we would call this a homomorphism if it achieved that goal. Over here, comparing these two tensors could never be the same. They're not the same spaces. Now, there are certainly tensors where they might be the same space. If you go to geometry, that happens all the time. A dot product, right? I have a vector over here and a vector over here, and I multiply them together to see if they're perpendicular. That's homogeneous data. So then I might use the same function on both sides. Okay? But here, the supplies are different from the plants, are different from the clients. There's different spaces. They could even be different sizes, like vectors of size 2 or 3 or 10 or 20. Because they're not the same, you cannot use the same function on them. So then these have to be different.
So then for the multiplication, which is heterogeneous data, you
Yep.
still had the same F at the top as at the bottom.
No, I've erased, so I've helped myself out wonderfully. So in the scalar multiplication, I put the identity,
Right.
then I put F, and then because I did recycle V and U, I allowed myself to have F where they were the same spaces.
Okay.
But notice it's not F's everywhere,
Yeah, yeah, yeah.
right? So the point is, if you can recycle, then sometimes that's what you want to do. You recycle because you're not trying to find, I mean, sometimes you do need to be creative and really switch everything up. Something can be completely heterogeneous where nobody is the same. That can happen. It's just not the most common thing, because what we're looking for is, I already observe a pattern of taking this data to this data, and I want it to be compatible with everybody else's transformations. So then I stick it everywhere it can be used, and I see if it's compatible. And if it's not, I set it aside and don't call it algebra. You could study it some other way. It's just not going to be aided by the world of algebra. Okay, algebra has some advantages. We haven't proved anything with this, but once we have this working, we get results from it. That's the reason to pay attention to this. It's not because, well, define anything you want. Make the arrows go the other direction if you want. Like, whatever, right? Make your arrows, I mean, there's lots of things you can do. Which ones lead to good algebra are the ones I'm self-selecting for you, because then they'll prove things for us. Okay? Okay, help me finish out the purple here. Or what is this, pink? Pink. Help me finish the pink. What happens to V1?
It's your F1 of V1.
Thank you. It's a different function for each part, so I keep the indices on the functions as well. This part becomes
FL.
excellent. I apply the different tensors, gamma and upsilon. So gamma came down this way, upsilon, oops, it came out this way. Oh, come on, it has to happen once in a class. You know, you become a mathematician because you like doing math, and then you have to give lectures. And they're dry and they're boring, but then you discover this amazing thing. When a class is super boring like this one, anything you say is funny. Anything, because everybody's like, any small hint. There's no way that a comedian would think anything I did today deserved the laughter you gave me. But because I've made it so dry to this point, I just get that little pop of happiness. So. Okay. Two paths to the same location. If we want them to be called compatible, if we think we're going to do algebra with them, what should happen when they got to the same place?
They should be equal.
They should be equal. Now, when you do this, you start to pick up on this general feeling. Ignore the little subscripts of the ones and so forth. You kind of have a function on the outside with the operation in the middle, however you write that. And then that function gets to move inside, past the operation. I think of it like an osmosis layer, right? Like there's particles on this side and it's kind of trying to dilute the substance on the other side, just move through, right? And so that general philosophical change is capturing the translations that will be good for algebra, that lead to predictions you can make, okay? That's the key idea. If you don't have this equality at the end, you run the risk of making things that don't relate to each other. The whole story of algebra is taking one person's operations and making them equal. Specifically the word equal, not less than or that's analysis. There are other things to study. Equal going to equal, that's when it's algebra. One set of equations being compared to another set of equations gives you an advantage to study the equation two different ways. Hopefully one is easier. Then you can take what you learned in the easier land back to the harder land and say, I have new fire. Right? That's the whole algebra game. That equality is what we need to call these compatible, or a heteromorphism, or the technical word for these is a heterotope, heterotopism. Don't, just call it compatible, okay? Fancy words don't help you actually talk to people, okay? All right. We don't have much time, but we have 5 minutes to start our journey back to fundamental spaces. There'll be a lot of barns in this class. That's a house, not a barn. Some happy horses live in there. This is some vector space. I'm drawing something so that I can picture what's going to happen here. That house, I'm now going to photograph. It's an old-timey camera. You have to sit behind a curtain, take the lens cap off. And you get the little picture of the house. This is a transformation of one vector space to another. Everything in here could be described as coordinates in three dimensions. Over here, they could be described as coordinates in 2 dimensions. Hold on a second. Let's have more fun. This is actually hanging on the wall inside of the house. So it's really 3 dimensions back. Okay? You don't think that's right? You don't like my drawing? Are you going to come up here and do better? Okay. Now, this transformation took one vector space to another vector space. Does it work compatibly with the operations? Now, oftentimes the difficulty here is that it's super easy to write down algebra that looks like other algebra. But that's not the data we're actually talking about. I'm talking to our management team. They're talking in terms of suppliers. They're not talking about vectors in addition. You're taking some geometry and you're comparing it to another geometry. Visually, you know what's going on. That's not pluses and minus signs. Functions come to us in lots of ways. And we have to understand, are they producing something compatible? This is why we need to think geometrically and algebraically to be successful at linear algebra. What are some words we used in the beginning of the course when starting to talk about linear stuff? We had homework on it. Lines. Lines were something we talked about. Lines did what to each other? They could intersect at a point. They could also not intersect, which would mean they were parallel. So you know the language that you're actually talking about. You've known it for your whole lives. But we actually know a little bit more. When I talk about parallel lines as algebra, that means the slope is the same, right? Those would be parallel. They wouldn't meet because they have the same slope, whatever that slope is, but they're shifted up and down differently, right? Okay. If I'm going to preserve addition and scalar multiplications, if when I apply f to it, it literally just applies f and says, oh, this is f of y is now equal to scalar pulls out, right? And I do that to the other one. Scalar pulls out. What is the resulting line? Are they still parallel? That's a 7, sorry. Are they parallel? Absolutely. If parallel just meant they have the same slope, they still have the same slope. The fact that the algebra is compatible means that whatever algebra you've attached to geometry did not change when you applied this compatible function. So therefore, if I want to compare these and think about the underlying algebra, then to say that they're compatible should mean that things like parallel lines go to parallel lines. That intersections go to intersections. Oh, that's something I can visualize. When I take a photograph of the front of my house, am I sending parallel lines to parallel lines? Yeah. Am I taking intersections and keeping them intersected? Let's pick up with that on whatever. There's another class, and we'll pick up there.